Howdy and welcome back. In this video, I wanted to quickly review the adjacency list representation and then get into some considerations for actually implementing its structure in the C++ programming language. So to begin, adjacency list representation. The adjacency list representation of some graph G is going to be a set of vertices and a set of edges where every vertex from V is going to have an adjacency list. For each vertex from V, the adjacency list is going to contain all the vertices V such that there is an edge between them in our collection of edges. While this representation uses less memory than the adjacency matrix, we must search the adjacency list to determine whether a connection between two vertices exists. So we don't have that constant time lookup to see whether or not an edge presents. We actually have to go out to say, I don't know, one's adjacency list here and begin looking through. So if we wanted to know, hey, is there a connection or edge rather between 1 and 4, we'd have to iterate through its adjacency list and see whether 4 is within it. And it is. Let's say we wanted to see if there was an edge between 1 and 5. Well, going back to the adjacency list, we'd go back through one by one, and we'd eventually arrive at one past the last element in that list, and that would indicate that there was no edge between those two vertex. So the question is, how can we begin coding this up in our C++ program? So how can we implement a graph represented by an adjacency list in code? Given that a graph can consist of several vertices and each vertex can be connected to neighboring vertices, we want to map a vertex to a list of all its neighbors. So given, maybe vertex 1 here, how could we go from 1 to 1's adjacency list? We want a mapping, 1 being the key, the adjacency list being the value, and guess what's going to be appropriate here? An std map is going to allow us to map that key to a value. Therefore, we can map a vertex or its addresses to a standard library list comprised of its neighboring vertices or their addresses. So looking at this, imagine we have a collection of vertex stored somewhere in our program. And let's not focus on any connections between this. Let's say this pink object lives out there at this address in memory, the blue one at that, so on and so forth. If we have a collection of these, say, dynamically allocated objects, one way how we refer to them is through pointers which store their address. So one representation might be to have a map that's going to have as the key value a pointer to some vertex. And then what it's going to map to is going to be a standard library list of vertex addresses. So if we wanted to see if this yellow object was connected to the red one, we would simply use that yellow object's address as the index into our map. That would give us back its adjacency list, to which we'd iterate through one by one until we either find the value that we're asking whether or not is adjacent to it, or I guess object, or we arrive one past the last element within that list. So just, thinking about this, there are a number of different ways how we could represent this. Maybe instead of having the key in our map be an address, maybe it was that actual object to begin with. And then maybe the adjacency list is going to store just addresses as kind of previously discussed. So what's interesting here is, since we're dealing with C++, is how, if we're dealing with a collection of dynamically allocated objects, you quickly get into different considerations where you might have a dangling pointer and different memory management considerations that you'll need to make during your implementation of your graph with the adjacency list representation. So we're going to provide a simplified representation is what we're going to implement today, so that you don't have to worry about dynamically allocated objects. You don't have to worry about memory management. We're going to make it very straightforward to provide you the foundation to go ahead and scale up to more complicated representations. And we'll begin this in our next video.